Okay, let's jump back into these TVM in-class practice problems. We got through 1 through 6 in our first session. Today we're going to start up with problem number 7. All right, number 7 says that Stephanie plans to go to graduate school. She wants to have $40,000 saved for college expenses before she starts. If she can earn 4% compounded monthly while investing $750 per month, how long will she need to save at the beginning of each month to reach her goal? All right, so we're starting to get some new things coming into the equation here. So the first thing we want to ask ourselves is, do we have a payment? And the answer is yes, right? We have this $750 per month payment. And so we need to figure out the period in which that payment is taking place. And it says that Stephanie plans to save at the beginning of each month. And so in our calculator here, we definitely want to make that adjustment to make sure that we're set up to the beginning periods. The next thing we want to know is, does interest compound more frequently than annually? And here we see again that we have 4% compounded monthly. Even if it didn't say that, we would need to make an adjustment so that our payments and our interest rate were in the same periods. Remember, payments, interest rate, and term all have to be in the same units. So if we have a monthly payment, we also need a monthly interest rate. And when we calculate how long it'll take, it will show us how many months Stephanie's going to need to save the $750,000. All right, then the last thing we can ask ourselves is, what are we looking for? Well, we just answered that question, and we want to know how long. So we're looking for our number of periods here. Okay, so I've got this set up in Excel already. And so you can see our setup. And so let's go ahead and work this in the calculator, and then we'll come back and we'll work this in Excel. All right, so as of right now, well, before I get into this, I'm going to do what I told you guys to do. And let's change this calculator. So I need to hit second payment and then second enter. That gets me to beginning. And then I can clear it twice. And I'll notice that I have a BGN up here now, which means that I'm set to beginning mode. Okay, now we can start entering the things that we need to input to calculate this answer. So 0 is my present value. $40,000 is the saving target. So that is my future value. We have an interest rate of 4%. So I'm going to say that this is 4 divided by 12 equals IY. So if I need to convert my interest rate in a problem to where I'm trying to get my payment, my term, and my interest rate into the same periods, then my interest rate conversion will always result in me dividing my interest rate. All right, so that's what I did there. 4 divided by 12 equals IY. All right. Now that I have that input, we can come and input our payment. So our payment is $750 a month. And again, that payment is an outflow, so we'll make it negative. And then we can compute our N. Okay, so our N tells us it's going to take about 49 months for Stephanie to accomplish this goal. All right, so just a little over 4 years. Right, to get that back to years, we can just take our 49, which we know is months, divide it by 12 months in a year, and it gets us back to approximately 4 years. But Stephanie doesn't really want to know how many years. She wants to know how many of these payments does she need to make to reach her savings goal. And so that would be 49. All right, so now let's calculate this in Excel. So let's just go equals, and we'll choose our number of periods function. If you don't find that one for some reason, remember you can just go to more functions and search in PER. We already have it here, so let's just click on number of periods. And now I'm just inserting things into the box. Okay, so my interest rate is the 4%, but remember, we're converting this to a monthly rate. So we need to divide that 4% by 12. Our payment, we said, is the negative 750. Our present value is 0. Stephanie is starting with no money. Our future value is the $40,000, and our type here is a 1. Okay, so this is a payment that takes place at the beginning of the month. 1 means beginning, and we can hit done, and we get the same answer here, right? 49.02 months. Okay, well, let's move on, and let's take a look at number 8. Number 8 says, Ashley just completed her college degree and is ready to start paying off her student loans, which total $15,000. The loans have a combined annual rate of 4.5% compounded monthly, and it must be paid off in 5 years. How much will Ashley need to pay at the end of each month? Okay, so do we have a payment? Yes, but we don't know what it is. All right, that's what we're going to be calculating. But we do know that that payment takes place at the end of the month. Okay, that's good. So if we're dealing with a monthly payment, that means that we also need to have a monthly interest rate, which it says here that the interest rate is compounded monthly. And so that aligns nicely. And we can pretty much go to work here. We know we're looking for payment, and so we can input this problem. Okay, so I'm just going to clear off my TVM real quick, and I'm going to work this problem. Remember, the present value, anytime we're dealing with a problem that's working on loans, is going to be the loan amount. Now, before I start entering stuff, I just remembered here I'm set to beginning. This says the payment takes place at the end of the period, and so we need to change our calculator back. So we can hit second payment. That tells us what we're set to. Second, enter, and that changes it to the other mode. Okay, so now I'm back to end. I see that the top display of my calculator is clear. There's nothing there, so I know I'm set to end from that perspective as well. Okay, now let's put this in. 15,000 is our present value. 0 is our future value. We're going to pay this loan off. Our interest rate is 4.5 divided by 12, which equals our IY. Our term is 5 years. And so if we want to convert our term, then we need to multiply. So we have 5 years times 12 months in each year equals, that's our N. All right, and now we can compute our payment. All right, so if Stephanie, or I'm sorry, I forget this person's name. If Ashley wants to accomplish this in 5 years, then her payment is going to be $279.65 per month. Okay, so now we can go to Excel and we can do the exact same thing. This equals, this is a payment calculation. All right, so our rate, and I need to make this bigger. You'll notice here, my rounding is just a little bit off in Excel. When I click on that cell, the box tells me our rate equals 4.5%. Okay, we need to divide that by 12. Our number of periods is the 5 years. We need to multiply this times 12. Okay, so now I have a monthly rate and I have a monthly number of periods. Our present value is the 15,000. Our future value is 0, and our type is 0. The payment's taking place at the end of the month, so we hit enter, and again, we get an outflow of $279.65. Okay, let's take a look now at number 9. Kristen makes a $440 auto payment at the end of each month. Just a little side note, anytime you're dealing with loans, we were just looking at a student loan, now we're looking at a car loan. What you'll notice is that the payments for both took place at the end of each month. That's very typical. Most loans are ordinary annuities where the payments take place at the end of the period. All right, so Kristen's making $440 payments each month. If the interest rate on her auto loan is 7% compounded monthly and the loan is for 5 years, how much did she borrow to buy the car, right? So this is asking us what was the original loan amount, which means we're calculating a present value. All right, so payment takes place at the end. My calculator's set to end. I can tell that already. And so I just want to start entering this information. So we had a $440 payment. Again, this is a loan, so our future value is going to be 0. Our interest rate is 7 divided by 12 equals IY. Again, looking at monthly payments, so we need a monthly interest rate. And our term is 5 years times 12 equals our N. Okay, so now we can just compute our present value, and we get $22,221 as the loan amount for the car. And so if we interpreted this backwards, what we basically say is that if Stephanie had a budget of $440 per month the maximum amount she could borrow is $22,221. Okay. Now, that doesn't necessarily mean that's what the cost of the car is. That's just the borrowed amount. So Kristen could have had a trade-in, or she could have had a down payment. We don't know any of that. We just know that this is what Kristen borrowed. Okay. So we can do the same thing in Excel, equals. Now we're going to be doing a present value calculation. Okay, so our rate is the 7% divided by 12. Our N, oops, sorry, don't do that. Our N is the 5 years times 12. Our payment is the 440 outflow. Our future value is 0 on the loan. And our type, again, is 0 for end of the period. We can hit enter, and we get the same thing, right? $22,221. All right, let's move on, and let's take a look at number 10. Okay, so Kevin is the beneficiary of a life insurance policy. He has the choice of receiving a lump sum of $500,000 today, or he can receive a $25,000 check annually starting today for the next 25 years. If Kevin can earn 6% on his money, which option should he take? Well, this feels like a two-step problem to where I'm going to have to work two different TVM problems to get to my answer. That's not necessarily the case. And the reason we can do this in one step is because for the two options, right, the $500,000 lump sum today or the stream of $25,000 payments over the next 25 years, right? For one of those options, we already know the present value, right? The lump sum present value today is $500,000. There's nothing we need to do to calculate that. And so if I want to do this in one step, then all I need to do is figure out the present value of the stream of payments over 25 years and determine which one has the higher present value. Okay, that's the easiest way to do this. There's multiple ways to do this. Just for fun's sake, another way you could approach this problem is you could calculate the future value of $500,000 25 years from now if Kevin earned 6% on his money. Or you could calculate, I shouldn't say or, and you could calculate the future value of 25,000 invested for 25 years, earning 6%. And you could see, does the lump sum value or the stream of payment option have a greater future value? But that requires two calculations. And so anytime we can simplify things to one calculation, we'll be better off because it takes less time and you get essentially the exact same result. Okay. I do want to go back to this really quickly. We need to figure out, because we do have a payment in our calculation, what the timing of that payment is. And so it says he can receive $25,000 check annually starting today for the next 25 years. All right. So what that tells me, if that stream of payments is going to start today, then that payment takes place at the beginning of the period. Okay. So we need to set our calculators to beginning. All right. So looking at number 10, we're trying to solve our present value again. Or I'm sorry, I'm in Excel. I need to come over here to the calculator. All right. So we have an interest rate in this situation. Goodness, I forgot. I think I might have a rounding error again. 6% on his money. I put this in wrong. Sorry, I'm using this as my cheater today. Okay. So we have payments of $25,000, and these payments are inflows. All right, I have a term of 25 years. I have an interest rate of 6%. No conversion here. This is all taking place annually. And I have a future value of 0. Okay, basically what that means is that once the 25,000 payments have been received over the 25-year period, there'll be no additional payments. There's nothing left over after all of those receipts. And so our future value is 0. Okay, now if I do that, I can compute my present value. I'm going to tell you right now, this is the wrong answer. And if we were in class together, I would say, why is this wrong? And I hope that somebody would say, It's because you work this at the end of the period instead of at the beginning of the period. And I would say bravo, right? Very good. That's the exact right answer. So do I have to start over again is the question. I actually did this intentionally just to show you this. I do not need to start over again, okay? Remember that every time we enter things into the calculator stores those functions. Okay, so it stored everything that I entered for my TVM functions. And so if I want to know what the present value is at the end of the period, all I need to do is change the timing of those cash flows. So I can hit second payment, second enter, and we can change that to beginning, right? And then all I need to do then is hit compute present value. Okay, so that is the right answer. Now, again, it's just taking what we entered into our TVM functions already to calculate that response. The reason I showed you that is because if you ever get in a bind, you're like, oh, dang it, I didn't change my beginning and end setting. I wanted to save you some time. Okay, so you can just change it, compute the function that you're looking for again, and it will take those stored values and compute that answer for you. Okay, so now we can look at the same thing here in Excel. Okay, so here we have equals. We're looking at present value. Our rate is 6%. Our number of periods is 25. That's the number of payments we're going to be receiving. The payment amount is 25,000. Our future value is 0. Nothing left after we receive $25,000 payments. And our type, again, it's going to be 1 for payments received at the beginning of the period. And we're done. Okay, so $338,000. So if we go back, the question says, which option should Kevin take? Well, if we compare the present values, the present value of the lump sum is greater than the present value of the stream of payments. And so in this case, if Kevin wanted to maximize the dollars received and the value of those dollars, then Kevin would take the $500,000 lump sum. Okay. All right, let's take a look at number 11. We're going to introduce something new here in number 11, which is the inflation-adjusted rate of return. It says Clay plans to travel the world in 5 years. He wants to have $35,000 in today's dollars for the trip. He thinks inflation will run about 5% annually for the 5-year period. If Clay can earn 7% return on his money, how much does he need to set aside at the end of each month? Okay, so we have something where we're dealing with inflation now. And so anytime we want to calculate the impacts of inflation on purchasing power, we need to calculate our inflation adjusted rate of return. All right. And we do this pretty frequently when we're looking at long-term goals where the amount of money needed needs to have a particular purchasing power. Okay, so Clay knows how much a trip around the world costs today. He's not exactly sure what the number of dollars will require 5 years from now. And so he wants to calculate how much he needs to save to have an equivalent purchasing power 5 years from now, which means he's going to need more money to purchase the same trip. All right, so let's do this calculation really quickly. Okay, so if Clay right now, well, let's do the inflation adjusted rate of return first, but even before we do that, let's change our calculator back to end because it says Clay wants to save at the end of each month. So for Clay, it said that he thought he could earn 7% on his investments, but he also thought that 5% was going to be the inflation rate over the savings period. All right, so when we calculate the inflation adjusted rate of return, and I'm just going to type this into Excel over here, okay? The inflation adjusted rate of return equals 1 plus the rate of return divided by 1 plus inflation minus 1 times 100 in the calculator, right? So we need to do this multiplication by 100 in the calculator because the calculator needs the interest rate to be in whole numbers. If we're doing this in Excel, though, we do not need this last part of the equation because Excel takes percentages for its interest rates. Okay, so calculator times 100, Excel, we just end it at -1. Okay, so that's the inflation adjusted rate of return. Okay, so now we can come to our calculator and work that. 1.07 divided by 1.05 equals -1 equals times 100 equals. Now, that is our annual inflation adjusted rate of return. It says that Clay plans to save monthly, and so we need to convert our rate of return to a monthly rate of return. So to do that, we can just divide that by 12, and that equals our IY. Okay, now we're pretty smooth sailing after this. Okay, so 5 times 12 gets me to 60 months, which is our end. $35,000 is our future value. Now you're probably thinking, wait a minute, you just said that he's going to need more than $35,000 in the future. Well, by inputting the inflation adjusted rate of return, I'm basically telling the calculator, when calculating the payment, tell me a payment that produces an inflation adjusted purchasing power equal to $35,000 today in the future. Okay, I'm going to say that a little bit different just to make sure I'm super clear. When I input the inflation adjusted rate of return and I tell the calculator to calculate a payment, what I'm saying is give me the payment that produces an amount of money that has a purchasing power equal to $35,000 today. All right. And so the calculator knows that I don't necessarily need $35,000. I need an inflation adjusted $35,000 purchasing power equivalent 5 years from now. Okay. And so $35,000 is our future value. 0, we're starting with nothing, is our present value. And we can compute the payment. Okay, so Clay needs to save $556 per month over the next 5 years to have enough money to pay for his trip. All right, and you say, okay, enough money. What is enough money? Enough money will be whatever number of dollars is needed in the future to have the same purchasing power 5 years from now as what $35,000 has today. Okay, well, let's do this same problem in Excel. You're probably starting to realize that Excel is easier than the calculator because everything is just laid out and sits in the function at one time. But here we go, right? So this equals our payment. Okay, so our rate, I calculated our annual inflation adjusted rate of return already. We can divide that by 12 to get a monthly inflation adjusted rate of return. Our number of periods is 5 times 12. Present value is 0. Future value is 35,000. Our type is 0 for end of the month. And we get to 556.46. All right, we're going to work a new type of problem now, and it's going to be an uneven cash flow problem. All right, so to do this, let's look at number 12. Dan is thinking of buying an auto repair shop. The purchase price is $50,000. The current owner tells Dan that he thinks he can expect the following annual profits after expenses at the end of each year for the next 5 years. $5,000 in year 1, $6,000 in years 2 and 3, $7,500 in year 4, and $9,000 in year 5. Dan thinks he could sell the shop for what he paid for it in 5 years. If Dan wants to earn 8% on his investment, should Dan buy the shop? All right, so the things that we've been looking at thus far all have what we call installment payments. Okay, so installment payments are those payments that we defined in our first video. A payment that is recurring and consistent for a set period of time. Okay, well, here our payments are inconsistent, right? The amounts vary. And so to deal with this, we have to use cash flow conventions or cash flow functions. And so we're going to look at two. We're going to look at the internal rate of return on cash flows, and we're going to look at the net present value of cash flows. Okay. So let's work this problem really quickly. Okay, so I just kind of laid this out in Excel so that you can see it while we input it into the calculator. Okay, so the first thing that we need to do when working cash flows is we need to hit our CF button. All right, and then we need to hit second clear work. Okay, that's going to get rid of everything that's in our cash flows right now. Okay, we don't want to be working with old inputs. With our TVM functions, I'm okay with just overriding stuff because there's only 5 things that could possibly have numerical values tied to them. So if I input a new value for each 5 functions, then I'm good to go. With cash flows, there could be a bunch of different values in there. And so I just want to go ahead and start with a clean slate every time I work a cash flow problem. All right, so let's hit that cash flow. Now you'll notice mine says 0. So the first thing it asks for is CF0. This is the initial cash outflow. All right. So CF0 in this case is 50,000. This is what it cost Dan to buy the shop. So we're going to make that negative because it's an outflow. And very different than TVM, every time we enter a number for our cash flow functions, we have to hit enter. Okay. So I entered negative 50,000 and then I hit the enter key. It's very important. If you don't do this, your calculator will not produce a solution. So for every single number we enter in cash flows, after we input that number, we have to hit enter. Okay, after that, we can go down. Then it wants to know what's the first cash flow. All right, so the first cash flow is 5,000. That's what the anticipated profit is for year 1. So 5,000, enter. Now you'll notice that's a positive number because we think that's going to be a cash inflow in the form of profit. Then we can hit the down arrow. Okay, the frequency of that cash flow, if we go back to here, is 1 time, right? 5,000 just happens 1 time. My frequency already says 1. Okay, so I can just leave that the way it is. I don't have to input anything. We can just hit the down arrow. Then it says, what's cash flow 2? Well, cash flow 2 is 6,000. All right, so 6,000, enter, and then down. Then it says the frequency of cash flow 2. Well, I can see here that cash flow 2 happened 2 times. So I want to hit 2, and then enter, and then down. Cash flow 3 is 7,500. So 7,500, enter, and then down. The frequency of that is 1 time, so I can just hit the down arrow. And then cash flow 4 is 59,000. So recall, the problem says that he thinks he can have a profit of $9,000 in year 5. And Dan also thinks that he could sell the shop at this time for what he paid for it. So we'll have the inflow from the profit and the inflow from the sale of the shop. And so this cash flow needs to be 59,000. Enter, and then we'll just make sure that our frequency says 1. Okay, so now we've input everything that we need for this cash flow problem. And so the next thing that we need to do is we need to compute the internal rate of return. Okay, so to do that, we can just hit IRR. Okay, and so it already gave me the answer, but you'll notice it says compute up here. Yours won't do this. I've already worked this problem in my calculator. So IRR equals, it's telling you to hit compute. All right, so if you hit this compute button, it'll produce this 12.95%. So our IRR here is 12.95%. Okay, and we're going to work that here in just a second, so I'm not going to enter that number. Okay. So once we do that, we can also calculate the net present value, right? This is saying, hey, listen, for IRR and NPV, we know what the cash flow values are. And so with the cash flow values known, we can calculate these things really quickly. And so now just hit NPV, and it's going to ask you for an interest rate. Well, it says that Dan would need an 8% rate of return to purchase this shop, okay? And so we can hit 8 and then enter. Okay, then we can hit the down arrow, and it's going to tell us to compute. So you can hit compute, right? And the answer is $10,203.79. All right, so what do these IRR and NPV numbers tell us? Well, if we go back to the problem, it says that Dan wants to earn 8% on his investment should Dan buy the shop. Well, IRR is telling us what Dan actually earned on the investment, right? So Dan actually is what, if these cash flows are true, Dan actually earns 12.95%. So this is greater than 8, which says, awesome. Dan should buy this shop if 8% is his minimum required return. This is anticipated to earn 13%. That's a good deal. What does NPV tell us, right? NPV tells us that this investment is going to produce returns $10,200 greater than what an 8% rate of return would produce. Okay, so when we're looking at NPV and we're trying to make a buy decision from an investment perspective, what we really want to know first is this number positive or negative? If it's positive, then we say, okay, that's a good sign because it's producing greater returns than the required rate of return. Okay, now if we want to interpret this more accurately, like I said before, this is producing returns of $10,203 greater than what would be produced by an 8% return, which isn't that surprising because our IRR is 12.95%. So we are generating more return than what is required. Okay, so the answer here is yes, right? With an IRR of 12.95 and an NPV over $10,000, then if Dan is looking at this investment opportunity, it looks like it is a good opportunity and he should consider buying that shop. All right, now let's do it in Excel, which again is much simpler. For this, we can just say equals, and I'm going to choose IRR. You probably don't have this, so let's just search more functions real quick, and we can search IRR and hit enter. All right, let's get that bad boy. And so it wants to know what values. And so I'm just gonna select my cash flows here. Okay, and then I'm going to hit enter. We're done. Okay, and it just tells me your IRR is 12.95%. Now, if you're getting this guess, you can input a guess here. You do not have to do that. I left that completely blank. I just input my values, and it told me that my internal rate of return is 12.95%. If I want to do NPV, I can do the exact same thing. This equals NPV. Okay, so I want that. Well, let's not do it that way. You guys like the box better. I know that from previous experience. All right, so let's look at NPV. All right, so the first thing it asked me for is your rate. So our rate we said is 8%. Has to be entered as a percentage, so 0.08. Then it wants to know the values. Here, we just want to input the value of our cash flows from profit, not our initial investment. So let's select these values. Okay. Sorry, I put those in the wrong box. Our values are those values. Okay, so 8's our interest rate, our cash flows, we've selected for value 1. And then at the end of this, we just need to say plus the first cash flow. Okay, plus the first cash flow, hit enter, and we get our 10,203. So again, for this, we've got our interest rate of 8%. We've got our string of profits over the 5-year period. And then we have our initial cash outlay added to that. And we can hit enter and we get that net present value. So calculator and Excel match up again. All right, just a few more, y'all. So thank you for bearing with me. I'm glad that this is a video and you can go back and pause and rewind and do all the things that you need to do with regards to breaks or rewatching something. I hope this is helpful. All right, so I skipped a number here. We're actually working number 13. It says Jack wants to receive $50,000 a year for the rest of his life. He has $900,000 today, and his life expectancy is 30 years. What is the minimum rate of return he will need to meet his goal? Now, this is a CFP board question, and it's tricky, right? It seems pretty straightforward. But if you overlook one thing, then you will get this problem wrong, okay? And that one thing is, what is the minimum rate of return? We don't know anything about what the timing of this $50,000 payment is. And so what this is intuitively telling us is that to get the minimum rate of return, you're going to have to choose the right timing of this cash flow. And so what we know is that if we take distributions at the end of a period, that gives our $900,000 more power to generate interest and other investment income, right? So the longer I can keep my balance as big as possible, right, the more valuable that balance is going to be, okay? And so in this case, we know that the minimum rate of return required to produce $50,000 a year is going to be if we take this $50,000 at the end of the year, because this thing is earning more money over time, which means that I don't have to have as high a rate of return to produce the same outcome. All right. So now that we know this, we can just go and rock this problem. All right. So back to TVM, walking away from cash flows now. I'm going to move this up just a little bit so you guys can see what we're working at the same time. So we have a $900,000 present value. Okay. When we're dealing with a saved amount, those savings are outflows, right? This is just the long-term effect of savings over time, right? So those savings were outflows. So we'll make our present value negative. All right. Our future value is going to be zero. We're assuming that we're going to spend all $900,000 by taking these $50,000 distributions. Okay. So our future value is zero. Our term is 30 years. Our payment is $50,000. Positive, right? We're receiving $50,000 as distributions. Now we can compute our IY. Okay. So the minimum rate of return is 3.67%. Now, if we wanted to prove that, we could just change this to the beginning, right? And we could compute our IY again. And if we took those distributions at the beginning of the period, it would take a 3.99% rate of return to produce the same outcome. Okay, so that's obviously not the minimum rate of return. This option is lower. And so that's why we set the calculator to the end. 3.67% is the return that we would need to produce $50,000 per year over a 30-year period from a $900,000 nest egg. Okay, so we can do that in Excel. Equals rate. I'm gonna do that over here. Sorry, guys. Okay, so our number of periods is 30. Our payment is the 50,000. Our present value is the 900,000. Future value is zero. This is going to take place at the end of the period. And if we format that, you can just right-click on that, and you can format your cell to a percentage with 2 decimal places, and click OK. Okay, so we get the same thing. All right, 3 more. Let's take a look at the next question. It says your client wants to purchase a new home for $400,000. Your client will finance $320,000 with a 4% 30-year mortgage. Okay, so again, the first question is, what is your client's monthly principal and interest payment? When we're calculating the payment on a loan, we want to know the loan amount. So a distractor in this problem is the purchase price of $400,000. This does not impact the payment, right? The payment is driven by the loan amount. And so when we input this, we want to use $320,000. Okay, so the first part of this is pretty straightforward. We've done this before. So we are going to be calculating the payment on this mortgage. So $320,000 is our present value. We're going to pay this loan off. So 0 is our future value. It says that we have an interest rate of 4%. So 4 divided by 12 equals IY. Remember, we're calculating a monthly payment. And then we have a 30-year mortgage. So 30 times 12 equals our N. Okay? So we have everything that we need. Our calculator is also set up to the end. Remember, I said earlier that loans are usually ordinary annuities where the payments take place at the end of the period. So we're in good shape here. So we can just compute our payment. And our payment here is $1,527 per month for principal and interest. All right, so if we come back to this, it says, how much interest would be paid in the first 24 months? And so to calculate this, we need to use our amortization functions. Okay, so you'll notice above the PV, you have this AMORT, that's our amortization functions. And so you can hit second PV, and it's going to ask you, what periods are we looking at? Well, it asks us how much interest got paid in the first 24 months. So P1 is 1, right? That's month number 1. We can hit the down arrow. All right, we need P2 to be 24. And so let's hit 24 and then enter. Okay, so if I go back up, I have P1 is 1, P2 is 24. We're looking at the first 24 months now. Okay, then I can hit down and the calculator is just going to calculate it for me. What this is telling me is that the remaining balance after 24 months on that loan is $308,500. The principal paid over the first 24 months is $11,500. And here's what we want to know. What is the interest? The interest paid over the first 24 months is $25,165. Okay, so the amortization functions are nice to be able to tell us stuff like this. All right, so the next thing that the question asks is, what would the loan balance be after 10 years? Okay, so again, we're in our amortization function right now. All we're going to do is set our periods up to tell us what this would look like over 10 years now. So I can go back up. P1, I'm still looking at month 1, except now I want to look through month 120, right? 120 months equals 10 years. So I'm going to change P2 to 120. So my evaluation period is the first 10 years now. And then again, I'm just going to hit down. And it says after 10 years, the balance would be $252,109. Okay, so these amortization functions are nice to be able to calculate stuff like this. Now, in the same way that we can do this on our calculator, we can also do it in Excel. So let's go ahead and calculate our payment. So our payment equals our rate divided by 12, our number of periods times 12, our present value, which is 320,000, our future value of 0, our type is 0. We hit enter. Okay, so the same $1,527. The next thing we want to calculate is our interest. Now, I already have all of the TVM functions that we inputted in the calculator shown in Excel. Okay, now when we want to calculate interest over time in Excel, we're going to use a function called cumulative interest payment. All right, so that's CUMIPMT, right? So this cumulative interest payment, you can just double click on that. And the first thing it's going to ask me for is what's your rate? Well, I already have my rate for this input here. Okay, so I'm going to input that rate divided by 12. Then it's going to ask me for what's my number of periods. Well, here it is from the previous calculation times 12. Okay, it asked me for my original loan amount. We got that, 320,000. Then it's going to ask me for my start and end period. So the start period is the first month. The end period is the 24th month. And then we can just hit done. Oh, wait. I think there, oh, got to scroll down. I'm sorry. Now we have to enter the type, which is 0. And then we can hit done. Okay, so it tells me the same thing, right? If I went back to my calculator here real quick, and I change this back to 24, interest is $25,165.27. Okay, so that's using our cumulative interest payment function. Now we can calculate our cumulative principal paid. Okay, so here we're going to calculate how much principal has been paid over the 10 years. So the function for this is cumulative principal. So that is the cumulative principal function. We can double click on that, and it's going to ask us the same kind of stuff. So what's your rate? We're going to use the rate that we use to calculate our payment. and divide it by 12. We're going to use our number of periods that we use to calculate our payment and multiply it by 12. Our present value is the loan amount. The start period is the first month. The end period is the 120th month. And again, we need to scroll down to pick up the type. Our type is 0, and we can hit done. And so this is telling us that the amount of principal paid over the first 10 years is $67,891. Okay, but we don't want to know how much principal is paid. We want to know what the remaining balance is. And so to do this, we can just say we want to say this original loan amount, and I'm going to add because I have a negative here, minus the principal that's already been paid equals our remaining balance, which again is what we saw when we made this 120. Our remaining balance is $252,108.67. And this also matches up, right? $67,891 in principal paid, $67,891 in principal paid. Okay, so that's how we use amortization, both in Excel and the calculator. For number 15, we're just going to work this in the calculator, not in Excel. So let's take a look real quick. It says, what is the effective rate of return of a nominal interest rate of 5% compounded daily? Now, the Consumer Protection Act that was passed in, I believe, 2010 said that all interest rates have to be reported as effective interest rates. And so an effective interest rate is one that already shows the impact of compounding. Okay. A nominal interest rate is an interest rate before compounding. Okay. And so we don't really have to worry about this anymore, but since the problem's in here, I'll show you how to calculate an effective interest rate using a nominal rate as your starting point. Okay, we're not going to do this in Excel. Okay, so we can hit our second key, and we can hit the number 2. You'll notice above the number 2, it says interest rate conversion. All right, it's going to ask you, I'm just going to clear this out real quick so that we can do this. It's going to ask you for the nominal rate. Okay, our nominal rate here was 5%. So after you hit the 5, hit enter, and then we can hit our down arrow, and it's going to say EFF equals. We need to go down one more time. Okay, this is going to ask me for how many compounding periods per year are you looking for? Well, we're doing daily compounding, so we need to hit 365 and then enter for daily compounding. Then we can go back up to EFF, and all we need to do now is hit compute. Okay, so this basically says if you have a 5% interest rate that compounds daily, then the actual interest rate that's being paid on money is about 5.13%. Okay, because as money compounds on top of itself, it earns additional interest. And so the more frequent compounding we have, the higher the rate of return over time. Okay, so that's how you convert that. Again, that's kind of obsolete based on the legislation that passed in 2010, but at least you know how to calculate it now. Okay, the last thing we need to do is number 16, calculate another inflation-adjusted rate of return just for practice. So it says, what is the inflation-adjusted rate of return of 7% and an inflation rate of 3.5%? All right, so this is just a straight calculation in the calculator. Again, our inflation-adjusted return, if we want to go back up here, is 1 plus our rate of return divided by 1 plus inflation minus 1, or if you're working on the calculator, you need to also multiply by 100. Okay, so I'm going to say 1.07 divided by 1.035 equals minus 1 equals times 100 equals an inflation-adjusted rate of return of 3.38%. Okay, so this is just important to recognize that inflation does impact the